Alrighty, it's 12:30, so let's get started with the roll. Grant Amerson. Brandon Ashlock.
Here.
Jacob Bouton.
Here.
Wade Burton. Claire Casadesis. Chandler Davidson. Juliana Damari. Cameron Dreyer. Brooke Edmondson. Julia Everett. Jack Foyle. Garrett Gresham. Daniel Hill. Brian Joes. Cade Leo.
Here.
Jacob Matthews. Dylan Miller.
Here.
Noah Perkins. Alexander Petty. Nicole Robles.
Here.
Tristan Sharp.
Here.
Joseph Saharath. Kinsley Spadafora.
Here.
Sophia, see you over there. Race Wickland.
Here.
Michael Martin. And Kendra Hayward, I see in front of me. All righty. So today we are going to begin to talk about transient analysis of first order circuits. And so that means RL circuits and RC circuits are on the table for today. Excuse me. So the first example that I've prepared is on the difficult side of straightforward, just because of the number of components and things like that. So we're going to take a formulaic approach to all of these problems, in as much as we're going to analyze the circuit at t is equal to 0 minus. Then, if necessary, and I'll explain what that means shortly, analyze the circuit at t is equal to 0 plus, calculate the time constant for the circuit, and then use all of those results to put into our generic equation for the response of a first order circuit. Mr. Sharp, you've raised your hand. How may I help you?
So there's been a couple of times I've gone back to try to see if I missed something. Are you posting or the recording somewhere?
They're all on the Meta Moodle page and have been the entire quarter.
Okay, I kept trying to look for it and it wouldn't show up. That's all. Thank you.
Yep. On the Meta Moodle page, it should be on the left-hand side. The lectures should be broken down by topic, and each individual link should have, like each individual topic should have the video lecture material. Is that correct? Is that how everybody else is finding it? Okay. Alrighty. So we're going to analyze this circuit at t is equal to 0 minus. Now, it's important to note that t is equal to 0 minus constitutes a DC steady state condition, okay? We are making the assumption here that in this particular case, that switch has been closed for a very, very long time. Oh, actually, I'm looking at the wrong problem. Let's start with the easy one. There we go. So we're making the assumption that the switch has been closed for a very, very long time, such that any time-varying transient signals have decayed to 0, and then we are opening that switch up, which causes the circuit to abruptly shift from a DC steady state condition into a transient condition. or transient just means things are changing. So at t is equal to 0 minus, we are going to replace our inductors and capacitors with their DC steady state equivalent. So does anybody remember from Dr. Harbor's lecture, I guess on Monday, what the DC equivalent of a capacitor is, since this is a capacitor problem? So you might be getting ahead of where we're going, but in a DC circuit, so just as a quick aside over here, the current flowing through a capacitor given by the capacitance value itself multiplied by the change in voltage. Okay, so at t is equal to 0 minus, our switch has been closed for a very long time. So our circuit is being excited by a DC voltage source and has been for quite some time. So we should expect that because our circuit was excited by a DC voltage source for a very long time, all of our currents and voltages in our circuit are also constant valued, right? So since the voltage over the capacitor isn't changing for all points in time up to t is equal to 0 minus, we could say that the capacitor current must then be 0, which means we're going to replace our capacitors with an open circuit. So in this instance, we'll have our 3 kilo ohm resistor, an open circuit where our capacitor was. This will be VC at time is equal to 0 minus. Excuse me. Our switch is closed at t is equal to 0 minus, so I'm replacing the switch with a short circuit. Here's my 12 volt source, resistor, resistor, resistor. Let's see, 4 kilo ohms, 12 kilo ohms, 4 kilo ohms, 8 kilo ohms, 12 kilo ohms, and our quantities of interest, which I've been putting in blue, so I'll continue to do that, are now VC at t is equal to 0 minus, as well as this current IR at t is equal to 0 minus. So this is a DC circuit, so it should be fairly straightforward to analyze. Nothing different than what we've done for the past several weeks. So that then begs the question of how do you guys want to approach the analysis of this? Again, keeping in mind that we're trying to determine that quantity VC at 0 minus, as well as that resistor current IR at 0 minus. Any thoughts on how we might determine either of those quantities? Let me ask you a slightly different question then. Are the two quantities related? For what I mean by that question is, if we observe that this current flowing through the 3 kilo ohm resistor is equal to 0 amps, which must be true because the 3 kilo ohm resistor is not part of a closed current carrying circuit. Let me move it to the outside actually, so it'll be a little bit easier for what I'm about to do. What does that tell us about the voltage VC at 0 minus? The voltage drop here is 0 volts. So VC at 0 minus could just as easily be redrawn as this. Does everybody understand why that capacitor voltage has the voltage drop over the 4 kilo ohm resistor, negative polarity on top? So the DC equivalent of a capacitor is an open circuit. No current may flow through an open circuit. If the 3 kilo ohm resistor is in series with an open circuit, then obviously no current can flow through it either. Right? So the 3 kilo ohm resistor does not form part of a closed current carrying path. So the current flowing through it has to be 0, which implies then that the voltage drop over it is also 0. So now that we know that the quantity IR at 0 minus and VC at 0 minus are inherently related, what circuit analysis method could we use to determine either of these quantities? Because once we know one, we can easily get the other just using Ohm's law. Anybody got any ideas? So it's a DC circuit. You guys have spent roughly 4 weeks analyzing them. Somebody say something. So Ms. Hayward suggested nodal analysis. So let's think about that real quick. What I'm going to do is identify my nodes and see how many I have and that kind of good stuff to see if that will help. So that's one node. Oh goodness, opened up Microsoft Store real quick. Dumb finger goes nuts. So that makes 2 nodes. Here's a 3rd node. And lastly, here's a 4th node. Since we're going to set one of them to ground, we could easily do nodal analysis on this circuit to determine that quantity VC at 0 minus. Our other option, mesh, would also result in a 3-equation, 3 unknown system. So here it really isn't any more efficient going nodal versus mesh. They're both of relatively equal difficulty. So since Ms. Hayward said nodal, let's run with nodal. Where would we want to set our ground? I'm sorry, what was that? On the green. Okay, I disagree. What were you saying, Kendra? Yeah, so the reason why I disagree with your statement, Mr. Foyle, is because if I put my ground here, then this node, let's call it VA, is given, right? No, I don't have to do any work for it whatsoever. Let's call this guy over here VB, and let's call this guy right here, conveniently enough, VC, which is going to be the exact same thing as the capacitor voltage we're looking for, right? So if I put it at the bottom, I run the risk of having to flip signs and do this, that, and the other to figure it out, whereas this way lets me explicitly determine the capacitor voltage directly as the nodal voltage, not as the difference between 2 nodal voltages or anything like that. Yeah, so determining where to put your ground is always a matter of preference, really, or where you can put it to try to make the problem more easy to solve. And in my opinion, putting it up here at this light blue node makes it more easy to solve. So that's where I'm going with it. Alrighty, so using our nodal voltage labels that we have, we know that for our supernode, we're going to have VA is equal to 12 volts, and that's it. If we perform Kirchhoff's current law at node B, we are going to have VB minus VA over 4 kilo ohms plus VB minus VC over 8 kilo ohms is equal to 0. And when we perform KCL at node C, we're going to have VC divided by 4 kilo ohms plus VC divided by 2 kilo ohms plus VC minus VA divided by 12 kilo ohms plus VC minus VB divided by 8 kilo ohms is equal to 0. So anybody see any mistakes in setting up my nodal analysis equations here? Yes, sir. Thank you. So that means that this guy is 12, right? Yes, thank you very much. Any other mistakes or anything anybody's noticed? I don't see any. I'm just trying to make sure that we don't screw this thing up. Okay, so we can solve this system of 3 equations, 3 unknowns, and in doing so, we'll get VA, VB, and VC, which is going to be equal to VC at 0 minus. So let's take a moment to solve this guy. So I have a 3x3 system where I'm being lazy. So in my second equation, my coefficient for VA is -1 over 4,000. My coefficient for VB is +1 over 4,000 plus +1 over 8,000. My coefficient for VC is -1 over 8,000. My constant term is 0. In my third equation, I have -1 over 12,000 for my coefficient for VA. -1 over 8,000 for my coefficient for VB, and then 1 over 4,000 plus 1 over 12,000 plus another 1 over 12,000 plus 1 over 8,000 as my coefficient for VC. Constant term 0. Solve. I get 12 volts. 9.333 volts, and lastly, DC as 4 volts. Anybody else get similar results? I got a thumbs up. So unless anybody has any objections, I'm going to move along to determine our resistor current IR at 0 minus. Anybody got any beef? All right. So to determine our resistor current, IR at 0 minus, we need only look at our relationships here, right? So IR is the current flowing into the negative polarity terminal of VC. So that means that IR is going to be negative VC at 0 minus divided by 4 kilo ohms is -1 milliamp. Any questions about our circuit analysis at T is equal to 0 minus? Nobody's saying much of anything, so I guess everybody is. Yes, ma'am. Pardon? Yes, what about it? 4 volts divided by, or -4 volts divided by 4 kilo ohms is -1 milliamp. All right, so I substituted in this value to there. All right. So because we're interested in a quantity other than the capacitor voltage, we are going to have to analyze this circuit at t is equal to 0 plus as well. So at t is equal to 0 plus, this is the instant in time immediately after the switch changed positions. So we are no longer at DC steady state, which means we can no longer treat our capacitor as its DC steady state equivalent, an open circuit. So what we are going to do is we know for a fact that the capacitor voltage cannot change abruptly in a circuit, because doing so would cause an infinite transfer of energy, which cannot happen. So if the capacitor voltage was 4 volts at t is equal to 0 minus, it needs to continue being 4 volts at t is equal to 0 plus. And we're going to model this behavior by replacing our capacitor with a voltage source, which is, I think, what somebody suggested earlier. So for our circuit, we're going to have a resistor. Our capacitor is going to be replaced with a voltage source. Now our switch looks like an open circuit because it opened up at t is equal to 0. Here is our original 12 volt DC source. So let's put my resistor first, and then we'll talk about exactly what's going on here. So mess this guy up here. So this is 4 kilo ohms, 8 kilo ohms, 12 kilo ohms, 12 kilo ohms, 4 kilo ohms, 3 kilo ohms. This is going to be our current IR at 0 plus that we are interested in. So let's talk about that capacitor voltage real quick. So we know that it had a magnitude of 4 volts, which is why we're going to replace it with a 4 volt source. And we also need to make sure that the polarities match as well. So the capacitor voltage is defined with a positive polarity on the left. So I'll put positive polarity on the left, negative polarity on the right, and there we go. So I want to be super duper clear about this. We can only replace the capacitor with a voltage source at t is equal to 0 plus. That single instant in time is the only time at which this replacement is valid. So it's not good literally anywhere else. Here is our capacitor voltage VC at 0 plus, which again, we know to be 4 volts because it cannot change instantaneously. So I'm just going to go ahead and write that down as a reference. So how might we go about solving for our current IR at 0 plus? Mesh analysis. Okay, that sounds perfectly reasonable to me. How many meshes do I have? Let's start there. 3. Absolutely right. I have one mesh right here. Let's call it I1. I have a second mesh right here. Let's call it I2. And I have a third mesh right here. Let's call that guy I3. Why don't I have a mesh including the 12 volt source? I heard several answers, but none of them loud enough or distinguishable enough for me to understand what they were. What was that? An open circuit, thank you very much. Yes. So a mesh requires that there be a closed current carrying path, and because there's an open circuit there, it's obviously not a closed current carrying path. What could we say about the current I3 right off the bat, just by looking at it? Are there any voltage, is there any voltage source or current source exciting any of those resistors? No, so I3 is gonna have to be equal to 0, right? We'd have 12 kilo ohms times I3 plus 4 kilo ohms times I3 plus 8 kilo ohms times I3. So 24,000 I3 is equal to 0 implies that I3 is 0. So we're really only going to need to focus on meshes 1 and 2 here. So let's start by writing our KVL equation for mesh 1. So we're going to have 3 kilo ohms times I1 plus 4 volts plus 4 kilo ohms times I1 minus I2 is equal to 0. Around mesh 2, we're going to have 4 kilo ohms times I2 minus I1 plus 12 kilo ohms times I2 is equal to 0. And we can solve these guys and find I1 and I2. So let's do that real quick. So for my coefficient for I1, I have 3,000 plus 4,000 is 7,000. My coefficient for I2 is negative 4,000. And it's going to be negative 4 volts when we move it to the other side of the equal sign. For my second equation, I have negative 4,000 I1 plus 16,000 I2 is equal to 0. And I get 2/3 of a milliamp, and I think it's 1/6, but let me double check. Yeah. 1/6 of a milliamp as my current I2. Anybody else get something similar? 2/3 of a milliamp being 0.000666, blah, 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 repeating. And 1/6 of a milliamp being 0.00016, and then the 6 repeats. All right, so we've got a couple of people verifying that that's correct. So using those two values, how can I determine what IR at 0 plus is? There's a small mistake there. So 4, I'm assuming you mean 4 kilo ohms. Right, so when you multiply resistance times current, does that give you current? Right, so it's just the difference in the currents, right? So it would be I1 because it's in the same direction as it flows through that 4 kilo ohm resistor branch, minus I2 because the mesh current I2 flows in the opposite direction as indicated by IR. So 2/3, so 4/6 minus 1/6 is 3/6 or 1/2 milliamp, or 500 microamps if that floats your boat. All righty. Does anybody have any questions, comments, or concerns about the analysis that we've done here at t is equal to 0 plus? Hopefully fairly straightforward. So that's one of the things about the transient analysis is that it seems like it's going to be difficult because everything is actually based on calculus-based relationships. But by picking apart the circuit at these specific points in time, we can actually just do simple DC circuit analysis techniques to figure out what exactly is going on. All right, our third step is to determine the time constant for our RC circuit. And so what we're going to do there is we're going to be looking at the circuit during the transient condition, meaning at t is equal to 0 plus or later in time. And we are going to be trying to find the equivalent resistance, because in this case, there's only one capacitor, so finding that part should be pretty straightforward, right? So find tau, which is equal to R equivalent times C equivalent for an RC circuit. So we know that CEQ is simply 50 microfarads because it's the only capacitor in the whole dang circuit. So that bit's fairly straightforward. To find our equivalent resistance, we are going to be looking at our circuit at t is equal to 0 plus, but we're going to be taking the capacitor out and looking in through the terminals that the capacitor left behind when we removed it. So this is nothing more than the Thevenin equivalent resistance with respect to that capacitor. Okay. Because we're finding the Thevenin equivalent resistance, we need to turn off all of our dependent sources, which is why I've replaced that 12-volt source with a short circuit. And then I have resistor, resistor, resistor. So let's see, 4, 8. So what is the equivalent resistance seen by the capacitor then during the transient condition? Anybody have any ideas? So let me ask, what is the equivalent resistance seen looking into those terminals where the capacitor was? So one thing that we might want to consider, does this right-hand section contribute anything? No, right? If we combine these, like it should be fairly easy to see that the 4 kilo ohm and the 8 kilo ohm resistor are in series, which would give us 12 kilo ohms in parallel with that 12 kilo ohm resistor. But we would see that effectively this open circuit right here is one of the terminals of that equivalent resistance combination of what I've circled in orange. So since that resistive path isn't closed, it can't contribute to the resistance seen by the capacitor. So knowing that only the 3 kilo ohm resistor, 4 kilo ohm, and 12 kilo ohm resistor that aren't circled contribute, what is my equivalent resistance? I would argue that it's the 3 kilo ohm resistor in series with the parallel combination of the 4 kilo ohm resistor and the 12 kilo ohm resistor. Does anybody disagree with that? Okay, so it should be fairly easy to see that the 4 and the 12 are in parallel because they share this node and this node, and then a 3 kilo ohm resistor must be in series with it because it doesn't share the other node. So this is going to give me six kilo ohms, which means our time constant tau is equal to Req of 6 kilo ohms times Ceq of 50 microfarads. So 6,000 times 50 times 10 to the minus 6 gives me 300 milliseconds. Just because I prefer to express it this way, the reciprocal of tau is then ten-thirds per second. So our last step in this particular problem is to put all pertinent information into the generic equation. So our generic equation is as follows. Y of t, where y is simply representing the response. So it could be a current or a voltage through any particular element, is equal to y at t is equal to 0 naught for t less than 0 naught. And it's going to be y at 0 plus e to the minus t over tau, t greater than or equal to 0 plus. This is our generic expression, and the previous steps were literally just figuring out the numbers that we're going to put into this expression. Okay, all first order transient analysis problems behave in this explicit way. It can't do anything else. So with this in mind, our capacitor voltage as a function of time is going to be, so what was VC at 0 minus? Look back through it. 4 volts, okay? And what was VC at 0 plus? Shouldn't have to look back through your notes for this one. 4 volts, right? The voltage drop over a capacitor cannot change abruptly. So if it was 4 volts at 0 minus, it has to continue being 4 volts at t is equal to 0 plus. So it'll be 4 e to the minus t over tau. This is why that over tau is the same as tau to the -1 power. So it's going to be negative 10/3 t volts for t greater than or equal to 0 plus. So we literally just pick the different results and drop them into our equation, and we're guaranteed to be correct, okay? As long as our DC circuit analysis was correct and stuff like that, we're guaranteed that this is right. For our resistor current, we can do the exact same thing. So what was our resistor current at t is equal to 0 minus? -1 milliamp for t is less than 0 minus, and it was half of a milliamp for t is equal to 0 plus, if I'm not mistaken. And it will have the same exponential decay as the voltage. So everything is going to decay at this rate defined by the time constant, regardless of whether it's the voltage drop or the current through capacitor, resistor, etc. It's all going to decay in this exact same way, or be a constant value of 0. So we've analyzed a fairly difficult circuit. Okay. But the steps that we have to take are very straightforward. We analyze the circuit at t is equal to 0 minus. Then analyze it at t is equal to 0 plus. And we can skip that step if we're only interested in the inductor current or the capacitor voltage, because we know those two quantities cannot change abruptly. If we're interested in literally anything else, we do have to analyze the circuit at t is equal to 0 plus. Our third step is to find the time constant for our circuit. And our fourth step is simply to put it all together in our generic equation. If you can do those 4 steps in that order, you're guaranteed to get it right every single time, okay? So any questions on that problem before we move along? We only actually have 10 minutes left, so I guess I'm not going to get to work the third problem. That'll be okay. Everybody okay with this one? Alrighty, so our second problem is a little bit more simple because there's not as much going on, but there is also a dependent source in there that's kind of monkeying around with things. Now we aren't given how the circuit looks like for t less than 0. So this is effectively what's going on after the switch has opened or closed. This is what we're left with in the transient. And we're asked to determine the voltage drop over our resistor, the 40 ohm resistor, if the energy stored in the inductor is 54 nanojoules. So we need to take apart some of these different things and figure out exactly what's useful and what's going to be unnecessary. So let's start by trying to figure out how we're going to get our final expression for VR of t. I think that's a good place to start, is trying to figure out how we're going to get what we're actually looking for. Does anybody have any ideas? All right, so nobody's saying much of anything, so let's take a look at a couple of things. In terms of IL of t, how much current is that orange current that I've just labeled? Okay, so let's call it 0.2, but yeah, IL of t over 5. So 0.2 IL of t. Alrighty. How much is the current flowing through the 10 ohm resistor in terms of IL of t? What was that? It's IL of t, yeah, all of it. So 1 IL of t flows through the 10 ohm resistor because that 10 ohm resistor is in series with our inductor, and the inductor current is defined as the current flowing through the inductor. So we just have 1 IL of t. So if we perform Kirchhoff's current law at that top node, how much current is flowing down through the 40 ohm resistor in terms of IL of t? So the current going into the node, 0.2 IL of t, must be equal to the current leaving the node, which is IL of t plus some other quantity x, right? So from this, x has to be what? Negative 0.8 IL of t, absolutely right. So based on that analysis, VR of t in terms of IL of t is going to be what? So it should just be the current, negative 0.8 IL of t, multiplied by the resistor value of 40 ohms, right? Just good old Ohm's law. So now let's talk about how we can get IL of t. That's probably actually easier than anything else that we've encountered in this problem thus far, okay? So we know that IL of t, at least for t greater than 0 plus, should be of the form IL at t is equal to 0. And I'm not explicitly saying 0 minus or 0 plus here, because we know that the current flowing through an inductor cannot change abruptly, so they represent the exact same quantity, right? E to the minus t over tau. So the only two things we really need to figure out then to understand how this inductor current is behaving is the value of the inductor current at t is equal to 0 and the value of the time constant. Once we know that, we're good to go. Everybody agree with that sentiment? All right, so who has an idea on how I might determine the current flowing through the inductor at t is equal to 0? I'll give you a hint, and it has something to do with the energy stored. So we know that the energy stored, that looks like an omega, not a W, and that's going to drive me nuts, is 1/2 L IL squared. So from this, using a little bit of algebra, we should see that IL at 0 is going to be equal to the square root of twice the energy divided by the inductance value. Anybody have any problem with the algebra that I've done? So I multiplied both sides by 2, divided both sides by L, and then took the square root. Alrighty, so from this, we're going to have the square root of twice 54 times 10 to the minus 9 joules divided by our inductor value of 48 times 10 to the minus 3 henries. I get 1.5 milliamps. Anybody verify that for me? Alrighty. So we now know what IL at 0 is. How are we going to find the time constant, right? So for an RL circuit, tau is equal to the equivalent inductance divided by the equivalent resistance. Well, the equivalent inductance is simply the 48 millihenries because it's the only inductor in the circuit. That's pretty straightforward. So what we're going to need to do is then to determine the resistance seen looking in from where the inductor was, which, let's see. This is IL over 5. And this guy is IL. So unfortunately, we have a circuit with a dependent source that we're going to have to be looking at, which is going to make this analysis slightly more difficult. So my question then is, obviously there are no dependent or independent sources in here, so we're going to have to use a test source method, right? So what kind of test source should I use? So should I apply a voltage source across the terminals or a current source across the terminals? Current source, alrighty. I agree with that statement. Because if we apply a current source here, we get to set IL to have a specific value, which is going to make our analysis a little bit easier. So then that begs the question, do we want the current source direction up or down? Down, alrighty. Which means we're going to be trying to find this voltage V-test positive polarity on bottom. And let's just use a 1 amp source for the sake of argument. So we know that this guy is now essentially a 0.1 amp source, right? So it should be pretty easy for us to figure out what that voltage V-test is. So I'm going to use nodal analysis. I'm going to put my ground here. I'm going to call this node VA and this node VB. Those are the only two nodes I have in my circuit. And it should be obvious then that VA is exactly equal to V-test in this configuration. Everybody okay with that? Alrighty, so let's do KCL at node A. So we have 0.2 amps is leaving, plus VA minus VB divided by 40 ohms. And then we have 1 amp entering, and set that equal to 0. So that's my KCL equation for VA. So to be clear, I took care of this guy, and this guy, the 3 different paths branching off of node A. For node B, I'm going to have 0.2 amps entering, so that's negative, that's not blank. Then I'm going to have VB minus VA divided by 40 ohms. And then lastly, I'm going to have VB divided by 10 ohms is equal to 0. So I'm taking into account this current, and this current, which are the 3 different branching paths from node B. So if I solve those 2 equations simultaneously, I can find VA and VB. So let's do that real quick. All right, so we have 1 over 40, negative 1 over 40, 1 minus 0.2. And then we have negative 1 over 40, 1 over 40 plus 1 over 10, and then positive 0.2. I get 45.333 volts for VA and 13.333 volts for VB. So using all of this information, REQ is going to be V-test divided by I-test is 45.333 volts divided by 1 amp is 45.333 ohms. So finally, then tau, that looks like a terrible tau, is LEQ over REQ is 48 millihenries divided by 45.333 ohms. Is 1.059 milliseconds, or you can say that tau to the -1 is 944.444 per second. And from this, we now know that, I'm in the room here, IL of t is 1.5 e to the minus 944.444 t milliamps, and thus VR is simply, again, negative 0.8 IL of t times 40 ohms negative 48 e to the minus 944.444 t millivolts. Negative 0.8 times 40 times 1.5 times 10 to the minus 3. Yeah, negative 48 volts. Okay, so it's 3 minutes until the next group is supposed to come in, so please wipe down your tables, and I'll work this last problem and put a video of it up online for you guys sometime the next day or so. It's just a simple-ish circuit which has sequential switching. So one switch closes at t is equal to 0, another switch closes at some later time, and we'll see how that affects the transient analysis. All right, so today we are going to be talking about transient analysis of first order circuits, meaning we're going to be dealing only with RL circuits and RC circuits. You won't get to do RLC circuits until circuits 2, if that's your bag of cats. Alrighty, so the first problem that I have here is on the complicated side of pretty straightforward, and I'll explain what I mean by that momentarily. But there's really just several components that's kind of making this thing a little bit more difficult, but the analysis steps that we are going to take are actually going to be very, very straightforward. Anytime really that we have a transient analysis problem, we are going to be doing just a few very simple things that will break the problem down into easily digestible bits of DC circuit analysis, which is what you've been doing in this class up to this point. So our first step is going to be to analyze the circuit at t is equal to 0 minus, which in this case means it's the instant in time immediately before that switch opens up, disconnecting the 12-volt source from the circuit. So at t is equal to 0 minus, our circuit is in what's called a DC steady state condition, which means that all of our inductors and capacitors will be replaced by their DC steady state equivalent. So can anybody recall what the DC equivalent of a capacitor is? What was that? An open circuit, that's absolutely right. So we know that for a DC circuit, we know that IC is equal to C dV by dt. So if the voltage isn't changing, then we know that the current should be 0, which is why we're replacing it with an open circuit. So our circuit at t is equal to 0 minus is going to look like this. Our switch is closed, so I'm replacing it with a short circuit. Let's see. Now I'll draw in my quantities of interest in blue. So I'm going to need to determine the resistor current at t is equal to 0 minus and the capacitor voltage at t is equal to 0 minus. So, does anybody have any idea how we might solve for either of those quantities? Okay. So something that we might observe that may be helpful. What is the current flowing down through the 3 kilo ohm resistor? Can anybody tell me what that is? I disagree wholeheartedly. It'll be 0 because there's an open circuit, which means the voltage drop over the 3 kiloamp is also 0 volts. So I can express VC at 0 minus as the voltage drop over the 4 kilo ohm resistor with a negative polarity on top, positive polarity on bottom, just using Ohm's law. So we can see inherently that the capacitor voltage and that resistor current are linked. So if we can solve for one of them, we can easily get the other just using Ohm's law. Does anybody disagree with that statement? So let's revisit my prior question. How might we go about solving for either one of those quantities of interest in blue? This is a DC circuit analysis problem. You guys have had roughly 4 weeks of DC circuit analysis. So somebody just spit something out and we'll probably run with it. So I think I heard mesh and I heard KVL. So mesh is multiple applications of KVL, so I'll consider both answers to be correct. So if we do mesh analysis, how many meshes are we going to have? Let's start there. 3, right? So we'll have a mesh current right here. Let's call that I1. A mesh current right here, call it I2. A mesh current right here, let's call it I3. Why don't we have a mesh current I4? Because of the open circuit, right? So in order for us to have a mesh, we need to have a closed current carrying path, and the open circuit means that we don't have that. So there won't be a mesh I4 to the right-hand side, or the left-hand side there. Alrighty, so doing mesh analysis, there are no current sources, so we don't need to worry about any super meshes or anything like that. So let's just start with KVL around mesh 1. So I'm going to have 4 kilo ohms times I1 plus 12 kilo ohms times I1 minus I2 is equal to 0. Around mesh 2, I have negative 12 volts plus 12 kilo ohms times I2 minus I3 plus 12 kilo ohms times I2 minus I1. And then around mesh 3, I have 12 kilo ohms times I3 minus I2 plus 4 kilo ohms times I3 plus 8 kilo ohms times I3 is equal to 0. I can solve these guys for I1, I2, and I3. So let's take a moment to do that now. So let's see, I have 4,000 plus 12,000 is 16,000 I1 minus 12,000 I2 minus 0 I3 is equal to 0. Then I have negative 12,000 I1 plus 24,000 I2 minus 12,000 I3 is equal to positive 12. And then in my third equation, I have 0 I1, negative 12,000 I2, and 24,000 I3 is equal to 0. Solve. And I get I1 is 1 milliamp, I2 is 4/3 of a milliamp, and I3 2/3 of a milliamp. Exactly right. So based on these results, IR at 0 minus is going to be what? So it's definitely going to be negative I1, right? Because the mesh current is flowing, when it flows through the 4 kilo ohm resistor, is in the opposite direction of that indicated by the current IR. So negative mesh current I1 is negative 1 milliamp. From this, BC at 0 minus is going to be what? So Ohm's law tells us that, yeah, so it's going to be the current first is flowing into the negative polarity terminal, right? So we're going to have negative IR at 0 minus multiplied by the 4 kilo ohm resistor is going to give us positive 4 volts, right? So negative 1 milliamp is positive 1 milliamp multiplied by 4 kilo ohms gives us 4 volts. So does anybody have any questions regarding the DC circuit analysis that we've done to analyze the circuit at T is equal to 0 minus? Any of the steps, if it was confusing, let me know and we can talk about stuff. Nobody is saying anything, so you either all get it or all dumbfounded by my circuit's ability. Yes, ma'am. Pardon? Exactly right. So because the current IR is flowing into the negative polarity terminal, that's where this negative sign came from. All righty. So our second step, and we only have to do this step when we're interested in a quantity other than the capacitor voltage or the inductor current, okay? It was defined. Okay, so let's explain again why I put the negative polarity on top. So in our problem statement up here at the very top, the negative polarity terminal is associated with that node. So that's why the negative polarity terminal is still associated with that node. The positive polarity terminal is associated with this node, which is over here, but because there's no voltage drop, we can transfer it to over here. Does that make sense? So we know that the voltage drop over the 3 kilo ohm resistor is 0, so the positive polarity terminal of our capacitor voltage can just slide down along that because that 3 kilo ohm resistor is effectively behaving as if it were a short circuit or not even there. All right, so second step is to analyze the circuit. at t is equal to 0 plus. So this is the instant in time immediately after our switch changes positions. So it was closed, so this is the instant in time after it opens up and disconnects the 12 volt source from the rest of the circuit, okay? So it's critically important to realize that we are now no longer at DC steady state because we have instituted some change, which is going to cause currents to change, voltages to change, etc. So for a large portion of our circuit is going to remain fundamentally the same. Particularly all of our resistors are still going to be doing their best at impeding the flow of current. But our switch is now open. So I'm going to replace that with an open circuit. Here's where our 12 volt source is. So one leg of that is entirely disconnected. So let's see, 4K, 8K, 12K, 12K. All right, so the last thing that we need to discuss is what is going on with the capacitor, okay? So I believe Davis covered with you guys on Monday the current and voltage relationships for capacitors. And part of those relationships is that the voltage drop across a capacitor cannot change abruptly, meaning that if the voltage drop over the capacitor at t is equal to 0 minus is 4 volts, then the voltage drop over the capacitor at t is equal to 0 plus has to also be 4 volts. Now, there is no regulation about the current that's flowing through a capacitor changing. It can do that as quickly as it needs to, and it can assume any value that it needs to. So we are going to model a capacitor at t is equal to 0 plus as a DC voltage source, because we know that it has a fixed voltage at this particular instant in time, but any current that needs to flow through it can. So I'm going to drop a voltage source in, and it's a 4 volt source, and the polarity of this voltage has to match the polarity defined across the capacitor, which is positive polarity on the left, negative polarity on the right. So we know then that VC at 0 plus has to be this 4 volts. So what we need to focus our attention on is finding our resistor current at t is equal to 0 plus. So how might I go about doing that? Okay. Can we do nodal? We could do nodal or mesh. Because we did mesh, I'm going to change to nodal here just for the sake of argument. Yeah, variety as well. Let's say 0 plus was 4 volts. All right. So that begs the question of where we should put our ground. Put it at the bottom. Right? So if we put it at the bottom, so let's label our different nodes. So that's going to be 1. That's our ground node. Oh, that's too close. I can barely tell the difference. Alrighty, so it looks like we have 1, 2, 3, 4, 5 nodes, not including our ground node. So in order to do nodal analysis here, we are going to need to make some circuit simplifications, at least to be able to handle it on our calculator. This particular problem, the simplifications are fairly straightforward. For instance, I can observe that the 4 kilo ohm resistor and the 8 kilo ohm resistor are in series. Anybody disagree with that? So I can call this guy that's terrible looking. A 12 kilo ohm resistor, and I can now see that those two 12 kilo ohm resistors are in parallel, right? So 12 in parallel with 12 is 6. So I now have 4 nodes. And that might seem like too much, but we'll figure out that it's probably not pretty easily. Okay, so I have a supernode. I actually have a couple of supernodes. So let's start actually with my voltage relationship equations. So let's call this guy node 1, node 2, node 3, node 4. So we know that V1 minus V2 is going to equal 4 volts. And we know that V4 minus V3 is going to equal 12 volts. If we apply KCL at our supernode, meaning that we're going to be taking a look at this current, and this current, we're going to have V1 divided by 3 kilo ohms plus V2 divided by 4 kilo ohms plus V2 divided by 12 kilo ohms is equal to 0. And now we have, one equation and a second equation that will allow us to calculate nodal voltages V1 and V2, which is enough information for us to calculate that current IR. So I'm going to stop writing equations because I don't need any more, right? So let's solve that 2x2 system and figure out what V1 is and V2 is. So my first equation, my coefficient for V1 is 1. My coefficient for V2 is -1. I set that equal to 4 volts. Then I jump down to the KCL equation, and I have 1 over 3,000 for V1, and then 1 over 4,000 plus 1 over 12,000 for V2. Set that equal to 0, solve. I get V1 is 2 volts with respect to ground, and V2 is -2 volts with respect to ground. So using that, IR at 0 plus is simply V2 divided by 4 kiloohms is negative 2 volts divided by 4 kiloohms is negative 1/2 of a milliamp. Anybody have any questions, comments, concerns about the circuit analysis that we've just done there? Alrighty. Our third step is to determine the time constant, tau, for our system, where for an RL circuit, or excuse me, for an RC circuit, tau is equal to the equivalent resistance multiplied by the equivalent capacitance. And it should be fairly straightforward to see that our equivalent capacitance is literally the only capacitor in our circuit, which is that 50 microfarad guy up at the top left. To determine the equivalent resistance is going to be a little bit more difficult. So I want to be very, very explicit here because this is a place where a lot of students get confused. When I'm determining the equivalent resistance, what I'm doing is I'm finding the Thevenin resistance with respect to the capacitor in this circuit during the transient condition, which means after the switch has opened. So what I'm going to have, so here's where the capacitor gets taken out. Whenever I'm finding the Thevenin equivalent with respect to an element, I take that element out. Here's my 3 kiloohm. Here's my 4 kiloohm. My switch is opened because we're during the transient condition. I have to turn off my independent sources because we're finding the Thevenin resistance. So by definition, I need to be looking at a dead network. Here is a 12K. Here is a 4K. Here is an 8K. And lastly, I have this 12K through the middle. Like so. So, does anybody have any ideas on how I might determine the equivalent resistance of this resistive network looking in as I've indicated with the arrow? Between at the set of terminals between the 3K resistor and the 4K resistor on the left-hand side. So this open circuit right here, I'm not looking in through there. I'm looking in through this way. Most certainly, yes. Do these resistors that I've circled contribute anything to the equivalent resistance? No. As we saw beforehand, I could shrink these guys down into a single 6 kilo ohm resistor, where one leg of that resistor is open circuited, so it's not going to contribute anything. So we really are only looking at how this guy, and this guy combine. So the 4 and the 12 are in parallel, okay? We can see that because they share this guy and this guy. Alrighty, so 3 kilo ohms in series with a parallel combination, 4 kilo ohms and 12 kilo ohms. So that is 3 kilo ohms plus 4 kilo ohms times 12 kilo ohms divided by 4 kilo ohms plus 12 kilo ohms. So 48 over 16 is 3. 3 plus 3 is 6. So from this, our time constant tau is CEQ times REQ is 50 times 10 to the minus 6 farads times 6,000 ohms is 0.3 seconds. And see why in a moment. I also like to look at the inverse of tau. So 1 divided by 0.3 is 10 thirds per second. So any question about how I determined the equivalent resistance for this particular network from the perspective of the capacitor? Anybody got anything to say? All right, so just to be super clear, it's always done during the transient condition, looking at a dead network. It's the exact same thing as the Thevenin resistance. All righty, our last step, 4, is to put all the pertinent information into our generic expression. So the generic expression that we have for our natural response problem, which is what we've been working today, is that y of t, which is a generic form of the response, meaning y of t represents our voltage or current of interest, because all voltages and all currents in this circuit are going to behave in this exact way, is equal to y at 0 minus, for t less than 0 minus, and it's y at 0 plus e to the negative t over tau for t greater than or equal to 0 plus. So how and why this works is, if you've watched the video, I derived how everything worked for particularly, say, the voltage drop over a capacitor. Well, Kirchhoff's voltage law is going to tell us that if one voltage has this exponential response, then all of the voltages have to have that same exponential response to be able to add up to 0. And then Ohm's law tells us that then all of our currents will also have that exponential response. So let's look. That is little t representing time divided by tau, which is our time constant for our circuit that describes the exponential decay. All right, so Vc of t. So what was the value of the capacitor voltage at t is equal to 0 minus? 4 volts. What was the value of the capacitor voltage at t is equal to 0 plus? It has to be 4 volts because it can't have changed. E to the minus t. So divided by tau is the same thing as multiplying by the inverse of tau, which is why I took the time to do this. So negative 10 thirds t volts for t greater than or equal to 0 plus. For our resistor current that we were looking at, its value at t is equal to 0 minus was negative 1 milliamp. Sorry, 0 minus. And then we're going to have positive, I think, let me double check there. Negative. So we literally just pull the information from our previous steps and drop it into our equation, and we're guaranteed to get the correct answer, assuming we were able to do the DC circuit analysis bits correctly, which, you know, it's nothing more than what we've done previously, right? We analyzed t is equal to 0 minus using mesh analysis. We could have just as easily done nodal analysis. At t is equal to 0 plus, we chose to do nodal analysis when we could have just as easily done mesh. It's just our basic DC circuit analysis techniques. Finding our equivalent resistance is the exact same thing as finding the Thevenin resistance, which we've done before. So all of the different steps of these problems are effectively review of the material we've already covered. We're now just putting those results into a specialized equation that tells us exactly how the voltages and currents in a transient analysis problem will work. So any questions regarding this guy? That is exactly right. So we could have just said, you know, t divided by 0.3, but I don't know, that seems weird to me, so I like to do it with I like to use the inverse of tau and multiply that by t. That's just my particular idiosyncrasy. E to the negative t over tau, 100% of the time. So in this case, because we have an RC circuit, this is y at 0 plus e to the negative t divided by RC. It's the exact same thing because we've defined our time constant to be R times C. So I think the very first thing I do in the next video actually is talk about time constants, but I didn't review the video before I came to class. So I'm using this generic expression which works for all first order circuits. So if it was an RL circuit, it will be y at 0 plus e to the minus t times r over L, where the time constant is L over R. Yeah. So all of these, if we do our generic expression with a tau in it, then we just have to say, find the time constant, and that's our third step. And the time constant has a different value for an RL circuit versus an RC circuit, but it makes our generic equation so generic that it works for every first order circuit. Right. All righty, so let's take a look at this next problem. We've introduced a little bit of difficulty here because we have a dependent source, which is going to influence how we determine our equivalent resistance. And I want to point out here that effectively this circuit is already at t is equal to 0 plus, okay? So we're given enough information to figure out what was going on at t is equal to 0 minus, and we're really just kind of looking at how this thing behaves beyond that point. So our ultimate goal is to determine the voltage drop over that 40 ohm resistor. Okay? So let's think about how we might be able to accomplish this goal. So before I lead the discussion, does anybody have any ideas about what we might be able to do here to figure out that voltage? All right, so let's call this current right here flowing down through the positive polarity terminal IR of t. Okay? Anybody got any problem? I'm just labeling a current at this point. Now, the current that I've drawn from left to right over that top left short circuit, how could I express that in terms of IL of t? This isn't supposed to be a trick question or anything like that. It's just IL of t over. So this current that I've drawn in orange is the current that's leaving that dependent source. So it's just IL of t over 5, right? So I'm going to call that 0.2 IL of t, because if I divide 1 by 5, I get 0.2. How about this current directed to the right through the 10 ohm resistor? how does that relate to the current IL of t? So the current flowing to the right through the 10 ohm resistor, just that specifically, how does that relate to IL? It is just IL, right? Because the 10 ohm resistor and the 48 millihenry inductor are in series, if IL flows through the 48 millihenry inductor, it has to also flow through the 10 ohm resistor. So I would argue that the current flowing in 0.2 IL of t is equal to the current flowing out, which is IL of t plus IR of t. And from this, we should see that IR of t is 0.2 minus 1, negative 0.8 IL of t. Anybody got any problem with that? You're observing what's going on and applying Kirchhoff's current law. We could use Ohm's law then and say that VR of t is going to be equal to IR of t times 40 ohms, which is going to be negative 0.8 IL of t multiplied by 40 ohms. Just Ohm's law there, nothing wild or crazy. So now we need to figure out how are we going to get IL of t. Well, this is a transient analysis problem. So we know that IL of t should be of the form, and we're only considering t greater than 0 right now. IL at 0, and I want to be clear here. Ordinarily, I would need to include either t is equal to 0 minus or 0 plus, but for an inductor current, those values can't change. They have to be the exact same thing, so I'm just going to designate it as IL at 0, understanding that it is that at 0 minus and 0 plus. E to the minus t divided by tau. So the inductor current is very well behaved. I just need to figure out what its value is at t is equal to 0, and then what the time constant is for the circuit, and I have enough information to figure out what's going on with that resistor voltage. So I've just broken this problem down into digestible steps to figure out what I need to do to get my final answer, okay? So how are we going to determine IL at 0? We're given some information there in the problem statement that says that the energy stored in the inductor at t is equal to 0 minus is 54 nanojoules. So how can we relate that statement of a known value of energy to a particular current? But we know the power that's being absorbed by, excuse me, the energy that's being absorbed by an inductor, right? WL is indicative of the power that's being, or excuse me, the energy that's being stored by the inductor. So what's the relationship between energy in an inductor and current through an inductor? You got your notes? Look at stuff we talked about on last Friday. So then it should be on the first page of stuff we talked about on last Friday. I think I went over. That's exactly right. Energy is 1/2 times the inductance value times the current squared. So we can algebraically rearrange this guy. So if I multiply both sides by 2, divide both sides by L, and take the square root, I get W at 0 times L, capital L. So just doing a little bit of algebra, I can manipulate that expression. And I will find when I substitute in my numbers that the square root of 2 times 54 times 10 to the minus 9 joules divided by 48 times 10 to the minus 3 henries gives me 1.5 milliamps. So anytime I know the amount of energy stored by an inductor, I know the amount of current flowing through that inductor as well. All right. So now we need to figure out what the time constant is. The time constant for an RL circuit is the equivalent inductance over the equivalent resistance. The equivalent inductance here has to be 48 millihenries because there are no other inductors. That's pretty straightforward. Finding the equivalent resistance is going to be a little bit more difficult because we have that dependent source. So here we have IL over 5. $40 ohms. I believe that's a 10 ohm. This is our current IL. And we're trying to find the equivalent resistance looking in through the terminals where our inductor was, okay? So this is a circuit containing a dependent source and no independent sources, which means we're gonna have to use a test source method in order to determine the equivalent resistance. So should we apply a test current source or a test voltage source? Well, we can, let me be explicit here. I think I covered this when we did Thevenin equivalent resistance and all that jazz. For the last Wednesday, I think. We can apply either and we will get the right answer regardless. But what is the smart choice here? I guess would be a better question. Voltage source, voltage test source, or current test source. So let me explain why it's not voltage. Okay. If I apply a current source, let's say direction down of 1 amp, what have I just done? I've set IL to have a specific value so that my dependent source no longer behaves like a dependent source, right? So this will be my test voltage that I'm trying to find. And I know that this guy is behaving like a 0.2 amp source. That makes my analysis pretty straightforward. So from that, how do you guys want to go about determining that voltage V-test? So I would say that you could do it using either nodal or mesh. You can't do it with a single application of KCL because there are too many nodes. And what I mean by that is we're going to see currents split up and then recombine and all that kind of stuff, and this is going to make it a little too nasty to just use KVL on. So would you prefer mesh analysis or nodal analysis? So I see what you're saying there. I would argue that it might actually make it easier. So let me explain what I mean by that, okay? we know both of those currents. So I guess we can do this with just one application of Kirchhoff voltage law then, actually. So let me explain what I mean by that. We know the current that's flowing through the 10 ohm resistor, right? 1 amp, which means we know the voltage drop over the 10 ohm resistor, 10 volts. We don't know the current flowing through the 40 ohm resistor. We can figure it out pretty easily, right? If 0.2 amps is flowing in, and 1 amp flowing out, then I would argue that 0.8 amps is flowing up this way. So we can write a very simple Kirchhoff voltage law relationship plus V40 plus V10 like so, and say that V test is equal to V40 plus V10. Everything in that here. Let me double check to make sure I'm not making some silly mistake. It's giving me a different answer than when I did it earlier, which worries me slightly. They're close, but they're off by like 1 1/3 ohm. I'm trying to figure out what simple mistake I'm either making now or I made then. I don't see anything obvious though, and I didn't write down any of the values wrong, did I? Let's start with something really easy like that. 40 and 10, 48. Yeah. Yeah, let's run with this. This seems like a more simple method. And again, the answers were really close. I feel like I just made a simple mistake in one or the other. But so if we set IL to be 1 amp, then IL divided by 5 is 0.2 amps. We know that's the amount flowing into this node. 1 amp is flowing out, which means 0.8 amps has to be flowing up through the 40 ohm resistor. We are all okay with that analysis. So defining our voltage drop over the 40 ohm resistor to where the 0.8 amp flows in the positive polarity terminal, and defining our voltage drop over the 10 ohm resistor such that the 1 amp of current flows into the positive polarity terminal, and writing a Kirchhoff voltage law equation where we would have V40 plus V10 minus V test is equal to 0, and rearranging we get the following KVL expression. V40 is 0.8 amps times 40 ohms, and V10 is 1 amp times 10 ohms. And so this should give us 0.8 times 40 is 32, plus 10 is 42 volts. So from this, REQ is V test over I test, 42 volts over 1 amp is 42 ohms. And then tau is equal to 48 millihenries divided by 42 volts. Over ohms, yes, thank you. Is 8/7 of a millisecond. Alrighty. And when I take the reciprocal of that, L to the minus 1 is equal to 875 per second. So we can put all of that information together to find that IL as a function of time for t greater than 0 is 1.5 e to the minus 875 t milliamps, and VR of t is then negative 0.8 IL of t, 40 ohms is equal to 48, negative 48, excuse me, e to the minus 875 t millivolts. And it ran 7 minutes long. So anybody have any questions regarding this problem? All right, so, pardon? Where our goal was to figure out what VR of t was for all t greater than 0 plus. And so we used Kirchhoff's current law to get an expression to put VR in terms of IL, which is what we did in the step in orange using Kirchhoff's current law, and then our step in blue is Ohm's law. And then from there on, it was literally finding out how IL behaves to be able to figure out how VR behaves. Yes, sir. So yes, that would absolutely matter. I made the assumption that IL was positive while flowing down, but if we had instead said that it was negative, then that would have changed our equations around slightly. When we applied KCL here, for instance, we would have had IR would have been positive 1.2 instead of negative 0.8. Unfortunately, unless you're told, there really isn't a way to know. So I just went with what I felt was the logical solution of we're going to get the positive value because it's defined in that particular direction. But you're absolutely correct that there is a second solution which would mess with things. Yes, you're 100% correct there. I just chose to ignore it and hope that nobody would notice, and you did. There really is no other relationship that we could have used, though, based on the information given to decide whether IL direction down is a positive quantity or negative quantity, other than it makes the most sense to me that it should be the positive value. Okay, so there is a third question here that we're not going to be able to go over because I'm already used up all the time I have and then some. So it is about, I guess you'd call it sequential switching. So if you can look at this real quick, you can see that there's a switch that opens at t is equal to 0 seconds, disconnecting that particular voltage source. And then there is a switch that closes at t is equal to 2 seconds, which is effectively switching in that resistor into the network. And so I'm going to work this one out myself after class and all that kind of stuff, and then put a video up online. This would be really significantly harder than anything I'd ever put on the test, but it is similar-ish to one of your homework problems. Probably a little bit more difficult than the homework problem, to be honest. But anyway, all righty, so you guys have a great rest of your day. If you wouldn't mind, clean your tables before you get out of here, and I will see you on Friday.